Hi everyone, welcome back to the channel. Today we're going to be looking at electronics cooling using natural convection or passive cooling. If you haven't seen my video on forced convection, I'll leave a link in the description, and we do a similar thing where we cool an electronic chip using forced convection. In this case, we're going to do the same cooling, but in a closed enclosure and just relying on passive or natural convection. So the problem we're going to set up today looks like this. Our domain is going to be analogous to having a closed enclosure which is mounted on a wall. And in the back of that enclosure, we're going to have an electronic board with a chip. So you can see our domain is going to be set up with an air domain with 4 individual walls all the way around, and then a chip located on the back wall. We're not going to have any inlets or outlets. This is going to be a fully enclosed system, and we're just going to let the air circulate inside this closed domain. Our chip is going to be supplied with 2.5 watts of volumetric heating, and our green faces here, or the external faces of our enclosure, are going to have 10 watts per meter Kelvin of natural convection, taking heat out of our enclosure and out of our system. The back wall is going to be adiabatic, or in other words, there's going to be no convection or conduction through the back wall of our domain. This would be analogous to our electronics enclosure being mounted on a wall or other insulating surface, where the heat loss into that wall or the surface behind is going to be minimal. Some other things that we're going to do today, we're going to do a 2D planar model, but this simulation and setup can easily be extended to 3 dimensions. And if you want me to walk through setting up this problem in a 3-dimensional array, let me know in the comments and I can make a video for that as well. We're also going to do a steady state simulation. Our viscous model is going to be using laminar flow modeling. And we're also going to use the energy equation to look at the convection in the system. And our working fluid in our enclosure is going to be air. We're also going to use a really cool mathematical way to represent the outside of the enclosure, which is 2 millimeters of aluminum, mathematically without explicitly modeling it in our system. And I'll show you how to set that up later. So before we hop over into Fluent, there's one really critical dimensionless number when you're setting up a natural convection problem. And that number is called the Rayleigh number. The Rayleigh number can actually tell us 2 things. It can tell us first how dominant natural convection is going to be in our system when we compare it to just diffuse conduction or conduction through the fluid in that domain. So the first thing we want to look for is, does our domain cross the critical Rayleigh number, and is natural convection worth looking at, and should we be modeling it? The second thing the Rayleigh number can also tell us is that if the Rayleigh number is above about e to the 9th, our flow will be turbulent. So the Rayleigh number looks like this. It's pretty simple. We can go through it quickly. The Rayleigh number states that the density times beta, or the thermal expansion coefficient, times the delta T, or the change in temperature, times a characteristic length cubed, times gravity, all divided by viscosity times thermal diffusivity of our fluid. If we solve that for our problem today, we have these values, as you can see here, for air at STP. And if we plug in all of our numbers, we get a Rayleigh value of about 3.41 times 10 to the 6th. So if we take that Rayleigh number and we look at the description that we were talking about before, we can see that our assumption of laminar flow should work well. It is not over that 10 to the 9th value for turbulent transition. And this 10 to the 6th number also crosses the natural convection threshold, which means that natural convection will be important for our problem, and we should track it in our problem. So without further ado, let's hop over into Fluent and we'll get this problem set up. So now that we have Workbench open, we're going to be using the fluid flow Fluent analysis system, so we can go ahead and drag that and drop that into our project schematic. First thing we're going to do is set up our geometry by clicking on the Geometry tab, right-clicking, and in this case, we're going to use Spaceclaim to design the geometry. So now that Spaceclaim is open, we can go ahead and start drafting our domain. Since we're doing a 2D simulation, we want to make sure that our simulation is located in the XY plane. So we're going to come up here to Design. We're going to go back to the 3-dimensional view and then reselect Sketch Mode and select our XY plane. We can now use the Cartesian coordinates in the bottom to look at that plane to give us a little bit better view. And now we'll go ahead and set up our problem. So the first thing we're going to do is I'm going to create our chip for our domain. I'm going to turn on Snap on Grid just to make drafting a little bit easier. And I'm going to go ahead and drag our chip here. Our chip is going to be 1 millimeter by 10 millimeter. Go ahead and select that. Next thing we're going to do is make our enclosure. So we can drag from this end, drag it out, and drag it up. And our enclosure is going to be 15 millimeters by 42 millimeters. Go ahead and click apply. So right now we're in the sketching plane. So these are just sketch rectangles. But if you see, if we go back to the 3D view, we're going to now have a surface. The next thing we're going to want to do is split these two surfaces so we have two separate cell domains in our simulation. The easiest way that I found to do this is by simply deleting our inside face by just hitting the delete key on the keyboard, going back into sketch mode, and just redrawing that rectangle. And we can go ahead and end sketching. And now what we'll see over on the left here is that we have two surfaces, one for the air domain and one for our chip. To make it a little bit easier to see, we can also select the color and change it to something so we can differentiate between the two surfaces. So now our domain is pretty much set up. The last thing we're going to want to do is make sure that we share the edges between these two domains and make sure that we can create coupled walls in Fluent. To do that, we're going to select on Design. We're going to come down here to our analysis and shared topology setting. And right now it's set to none. We're going to go ahead and set that to share. And now that that's done, we can go ahead and close out of here, go and mesh our model, and do our analysis in Fluent. So now that we're back in Workbench, we want to do one more thing before we head over into meshing. And that's changing our geometry from a 3D geometry to a 2D geometry. So to do that, we can select our geometry tab and go over to the right side of the screen here in the properties, and make sure that our analysis type, we switch from 3D to 2D. And now that that's complete, we can double click on meshing and go ahead and mesh our model. So now that we're meshing, we're going to start the same way we always start in meshing, which is naming all of our bodies and our faces. So we can start by doing the part select. We'll go ahead and select this big domain and we'll call that the air domain. And then we're going to select our chip and we're going to call that chip. The next thing we can do is start naming our walls. So as we said in the problem setup, our back walls here, including the back wall of the chip and the back wall of the enclosure, are going to be an adiabatic wall. So we're going to go ahead and label that as adiabatic wall. Click OK. And then our three remaining walls on our enclosure, so the bottom one, the side one, and the top one here, are going to be our enclosure walls. And we can go ahead and name them accordingly. The other thing I'm going to do here as well is name the walls or the interfaces between the chip and the air domain, and it will just make post-processing easier later. So now that that's complete, we can check a few things about our setup before we start meshing. The first thing we're going to want to do is click on our geometry tab, and we can come down here to the 2D behavior in the detail section. And we're going to actually change this from plane stress to plane strain. The next thing we're going to want to do is double check that our shared topology works. So if we look in the connections tab here, we see that we have no connections, which means that these walls are being shared between those two domains, which is perfect. The next thing we can do is just go ahead and mesh our model, leaving all the default settings in and just make sure that everything meshes correctly. So we'll go ahead and click update. And this is going to make a really coarse mesh, but it's always a good check to make sure that there's no glaring issues with your geometry that pop up right away. So now that meshed correctly, we can start refining our mesh and creating the mesh that we want for our analysis. The first thing I'm going to do is go to the mesh tab and down on this element size, I'm going to set a global element size of 250 microns. So that's 3 zeros and a 2.5. So that's the first thing we're going to do. We can go ahead and update and see how that looks. So by just changing the element size, you can see that our geometry was refined very well. We now have a very fine mesh through both our chip and our air domain. However, since we're doing both natural convection and heat transfer, we're going to want to make sure that we capture the boundary layers to capture the thermal boundary layer along the walls of our domain. So to do that, what we're going to do is right click on the meshing section, go to insert, and we're going to go ahead and insert an inflation layer. For this inflation layer, we're first going to have to select our geometry. So our geometry is going to be inside the fluid domain or the air domain. Go ahead and click apply. And the next thing we're going to have to do is select the boundaries that we want inflation layers on. In this case, we're going to want inflation layers on all of the wall in our simulation. So we can go ahead and go around and select all those boundaries and go ahead and click apply. We're going to make a few changes here to some of the settings. The first thing we're going to do is change the transition ratio to 0.77, and I'll show you in a minute how that affects our inflation layers. Next thing we're going to do is increase the maximum number of layers to 15, and we'll go ahead and leave the growth rate where it is. So we can go ahead and go back to the meshing tab. We can see that our mesh is now obsolete, which means we have to update. We'll go ahead and update and see how that looks with the inflation layers. So now that our domain is meshed with the inflation layers, we can zoom in and see what that looks like. So we can see that we have these really fine cells right up against the wall that slowly grow as we move away from the wall. So if we look back at our inflation settings, I mentioned that I changed the transition ratio from the default of about 0.27 to 0.77. What the transition ratio shows is the transition from the last cell of our inflation layers, which in this case is where my cursor is now, to our free stream cells or our global element size. We want to make sure that that transition is gradual as we move from these really small boundary layer cells into our free stream. And for fluid flow, in most cases, 0.77 or anything of a ratio of about 0.5 of cell face area between your top transition layer into your free stream is usually a good place to be. You don't want to go from these really, really fine cells directly into your bigger element size cells in your free stream. That can create problems with the simulation. Now that our mesh is refined adequately, we can go ahead and jump over into Fluent and start our analysis. So now that we're back in Workbench, we can double click on the Setup tab, which will open the Fluent launcher, and we'll make a few changes here. We'll first want to check that the dimension is defaulting to 2D, which is good. We're going to turn on double precision, which is a good idea anytime you're doing heat transfer of any sort. And we're also going to increase the solver processes to 4 and go ahead and click start. So now we're into Fluent and we can see that our mesh was carried over correctly. We can see our inflation layers came over okay, and both our air domain and our solid chip domain were carried over. First thing we want to do, as always, is use the perform mesh check option. So we can check our mesh elements, make sure it's okay, and then also check the mesh quality, which also looks good. Now that that's done, we can start working down the left-hand side and start setting up our problem. So in the general tab here, we're going to leave pressure based on. We're going to do a steady state simulation, and our 2D space is going to be defined as planar. We're also going to want to turn on gravity since it's the dominating force of natural convection. And we're going to set gravity equal to negative 9.81 in the Y direction, which in our case is the vertical direction. Now we'll move on to the modeling tab. In here, we're going to do two things. We're going to turn on the energy, and we're also going to switch our viscous model from SSTK omega to laminar. We can next go to the materials tab, and the default materials that come in to Fluent when you open are going to be air and aluminum, which is good. We're just going to change one thing in the air. So for natural convection is all based about density. So as a fluid heats up, the density changes a lot. And that change in density is what leads to the buoyancy and the natural convection of that fluid. So to get any air movement in our domain, we need to change this density from a constant value into something that's dynamic with temperature. In our case, the incompressible ideal gas is going to work well since our temperature changes are low and the effects of the compressibility of our air is going to be negligible. So we can go ahead and use that for our model. We're going to leave the default values for specific heat, thermal conductivity, as well as viscosity for the air, and go ahead and click Change and Create. For our aluminum, we're going to leave all those values as default. Next thing we're going to want to do is go down to our cell zone condition here, and we can see that both our cell zones are currently defined as fluids. We're going to leave the air domain defined as a fluid, but our chip domain is going to be solid, so we can go ahead and right-click on it, come down to Type, and change that to solid. So now our domain pops up here. You can see our material is already defaulting to aluminum. And the other thing we're going to want to do here is define the source term. The source term is going to be our heating of the chip. So if we come over to the source term tab, we can go to Edit, increase the number of energy sources. We're going to go ahead and use a constant source, and we're going to go ahead and set this to 250,000. Be careful to note here that the energy source term is defined as a watt per meter cubed. So it's the wattage or power divided by the volume of whatever cell you're applying to. So make sure you're not applying just the wattage of 2.5 watts here. And we can go ahead and click apply, and that's now all set. So we're going to have a source term and heating in our domain. Moving down our list here, since we have no inlets or outlets, there's going to be no inlet or outlet condition to set under boundary condition. But we can change all of our wall conditions in here. We're going to go ahead and do that now. So like I said, for the back wall or the adiabatic wall on the back, we're going to leave all the settings default. So we're going to set heat flux equal to 0, which means that there's going to be no heat leaving our domain through the back wall. For our chip wall here, so what we labeled as chip wall, which is the walls between the chip and our air domain, we can see that we have both the wall inside the solid and then the shadow wall inside the fluid. What this shows when we have a wall and a shadow wall combo is that we have a coupled wall. And if we open one of them and come over to the thermal tab, we can confirm that that wall condition is set to coupled, which is great. And we can leave that as it is. The last thing we're going to want to check is this enclosure wall. So these are our 3 outside walls of our enclosure. And we're going to change a few things in here. So what we're going to do is hop over to the thermal tab. We're going to use the convection thermal condition, and we're going to change 2 options. First thing we're going to do is we're going to change our heat transfer coefficient to 10. The next thing we're going to do is increase this wall thickness value to 0.002 and make sure that our material is defaulting to aluminum. What this is going to do is it's going to add mathematical resistance to these external faces and the heat transfer through those faces. In this case, we're adding a mathematical approximation of 2 millimeters of aluminum. This is a way that we can model the actual outside of the enclosure without actually explicitly modeling and meshing it, which can give us a big save up in computation time without the loss of much accuracy depending on the model that we're looking at. So with that said, we're going to go ahead and click apply, and that's good to go. So the next thing we're going to want to do is hop down to the methods tab here. And there's a few important things that we want to check. First, for most heat transfer scenarios, using the coupled scheme for the pressure velocity coupling is usually the recommended. So we're going to leave that as is. The second and very important thing that we're going to want to change is the pressure coupling. And we're going to change the pressure coupling to either presto or body force weighted. In this case, I'm going to use presto. When you're doing natural convection and you have that variable density and variable pressure, using second order can lead to some very poor modeling of the natural convection inside the domain with that variable density. It's recommended that you use either presto or body force weighted anytime you have a variable density of one of your fluids in your domain. And between the two, both of them work very well for natural convection. I just find that presto works a little bit better for me and for this case that we're setting up. So we're going to go ahead and use that. Next thing we can look at is our controls here. We're going to leave all of our controls untouched. Sometimes it's common when you're doing natural convection to drop the density a little bit, which can help your convergence. But in this case, we should be fine with the density under relaxation value set to 1. Next thing we're going to want to do, as always, is set up our report definitions. We want to look at those to make sure that our simulation is converging okay. And we're going to set up a few of them here. So we can right click on report definitions, go to new. First thing we're going to do is create a volume report, a volume average, and we're going to look at the temperature of the chip. So I'm going to call this chip temp. We're going to select our field variable of temperature and static temperature and select our cell zone for the chip. We're going to deselect this report file because we just want to look at a plot, but we don't need to export a file, and go ahead and click OK. Next thing we can look at is by again going to new. In this case, we're going to do a surface report, an area weighted average, and we can look at the wall temperature on our external faces of our enclosure. Again, we're going to select temperature, static temperature, and then select our enclosure walls. And once again, deselect report file and click OK. And the last thing that we're going to want to do is we can monitor the velocity of the air as it comes off our hot chip by putting a point into our domain and then looking at the velocity through that point. So to do that, we can come down to surfaces here. We can right click, go to new, and we'll go to new point. In my case, I'm just going to put this coordinates in. So we're going to use an X value of 2.5 millimeters away from our back wall. And then we'll set the Y value to about 10 millimeters above our coordinate reference. So as you can see, this is going to put a point right above our chip where we should be expecting hot air to be traveling up and then cooling down at the top of our enclosure. We can also give this point a name. So we'll call it flow point and go ahead and click create. Now, if we hop back to report definitions, we can go to right click, we can go to new, surface report, and look at the facet average. And we're going to call this point velocity. And we can go ahead and select the velocity and then look at the Y velocity, so the vertical component of the velocity, at the point that we created. And go ahead and click OK. So now that we have 3 report definitions, we can monitor these to make sure that our simulation is converging okay, along with our residuals when we get into the calculation. So with that set up, the next thing we can do is go ahead and double click on initialization, make sure that hybrid initialization is selected, and go ahead and initialize our setup. So now that our solution is initialized, we can jump over to the Run Calculation tab. We can go ahead and use this check case option to see if we made any obvious errors, which there are none. We're going to set the time scale factor to about 1.5 for the fluid, and we can set our solid time scale to 1,000. And we're going to increase the number of iterations to somewhere around 500. With all that set up, we can go ahead and start calculating our problem. A few things that we can check out here now that our solution is calculating. We can first look at our residuals, and we can see that those are slowly converging. We can look at some of our monitor points. So the first one we're looking at here is the chip temp. So you can see the temperature of our chip is actually gradually rising. We can also look at the wall temp, or the external wall of the enclosure, which you can see is rising up as well. And then we can also check our velocity at that point that we set. And we can see that that's going up as well, which is a good sign that our simulation has that natural convection and has the flow that we're looking for. So now we can see that our solution successfully converged, and we had to add a few extra iterations to converge past our convergence limit. So in this case, it took about 1,300 or so iterations to reach the 1e-6 on the or 1e-3 on the continuity. So we just added those to the number of iterations and reran the calculation. And now we can go through and check some things about our convergence. So first, if we look at the residuals, we can see that we have some nice decreasing slopes, which are taking a long time to decrease, so it takes a lot of iterations, but we are seeing a nice decline, which you always want to see in the residuals. We can look at our chip temperature, and we can see that it's coming up to about 330 degrees Kelvin, and it looks like it's leveling off, but not quite flat yet. Same thing with our wall temperature, only a few degrees increase to about 3.5 or so, and again, it's starting to flatten out, but not quite there. And finally, same story with our velocity. It's increasing to about 0.03 or so and starting to flatten out, but still hasn't quite plateaued. So with this stuff in mind, we can get a good sense that our simulation still hasn't fully converged. And the other thing we can check is if we go to the results tab up here, we can go to the flux section, select our total heat transfer rate, and select both our chip walls as well as our enclosure wall, and go ahead and click compute. And what we can see here is that this is showing us the heat flux between all these different surfaces. And if we come down here and look at the net results, we can see that we have a surplus of wattage in our domain, in this case about 0.0023 watts. What this essentially is error in our simulation. It's additional energy that we are not adding in, but with the numerics and all the other sources of noise, it's adding some additional heat to make the numerics work. We want to make sure that this net results for our flux is as low as possible. So this, coupled with our monitors of the chip temperature and wall temperature, show me that we still need some more calculations to get a more accurate answer. So to do that, we can come up to the residuals tab here. We can change our residual for the continuity down to something very low. So in this case, let's go to like 1e-8 and go ahead and click OK. And as we know, our simulation is converging pretty slowly, so we're going to bump this number of iterations up pretty high to maybe something around 3000, and then go ahead and click calculate again and let it run all the way down until it crosses that convergence criteria. So now our simulation is complete. We can click OK, and we can check out our residuals here. So it took us around roughly 3400 iterations to converge fully, and natural convection simulations can take a lot of iterations to converge accurately. So don't be discouraged if it takes a lot of iterations to get a good convergence value. So once again, we can go through and check our convergence here. So we can see that our residuals continue trending down and we're very smooth, which is great. We can check our chip temperature, which is flattened out nicely at somewhere around 330 degrees Kelvin. Same thing with our wall temperature, up at about 303, 303.5 or so, and that flattened out nicely as well. And finally, our point velocity as well is flattened out nice. We can also double check now our fluxes and our total heat transfer rate. Go ahead and recompute those values. And now we can see that our net result is really, really low, all the way down at about 1.86 e to the negative 8. So this is great. This is essentially showing that we still have a little bit of error, which is always common in a CFD simulation, but it's so low that it's not going to affect our values or our simulation accuracy. So now that our simulation is converged and we're happy with the convergence, we can start doing some post-processing. So the first thing we're going to do is we're going to come to the graphics window here. Go ahead and right click on contours and go new for contour. We're going to call this temperature. And we can select a contour of temperature. Look at the static temperature. We'll leave everything unchecked here. And the last thing I'm going to do is go to the color map options here. And we can change our color map from the default of field velocity and go to field temperature. We can go ahead and save and display. And we can see what's going on here. So we can see we have our hot chip up against the wall here. You can see that the heat is being carried off and going up and then slowly cooling as it hits the walls and then wrapping back around. And we're getting good convection through there and good heat transfer. To check that convection, we can go ahead and plot some vectors. So we'll go ahead and right click on vectors. We'll go to new. We can plot some vectors of the velocity, and we're actually going to color them by our temperature. So again, we're going to go to our color map options. We can change that definition to match our contour plot of field temperature. Go ahead and click apply. And the other thing we're going to do is we're going to scale down our arrows a little bit. So we'll go to about 0.2 and see how that looks. And we're also going to skip some. This will reduce the density of errors to make it more manageable to look at what we want to look at. So we're going to go ahead and skip 10 and see how that looks. So if we hit save and display, we can see exactly what's going on in our domain here. So we can see that our air is coming up. It's picking up heat and velocity as it passes our hot chip. It's going up in our enclosure. It's hitting those walls and cooling down, losing density and dropping back down and circulating nicely. The other thing we can check is we can look at our density values. So we're going to plot another contour here. Go to contours, again, new. We'll call this density. We can select a contour of density and leave it on density. And again, just leave everything deselected and click save and display. And again, this is another representation of our natural convection. So you can see our lowest density is right around that hot chip there as it picks up the heat and the gas expands and it moves up, starts condensing again as it cools down and then dropping back down through our domain and starting that natural convection current. The next thing we're going to do is create an XY plot by plotting a line through our chip and into our domain. And we can look at our thermal boundary layer over the top of the chip and also look at the velocity across that line inside our domain. We can do this by coming over to the Surface tab again, right-clicking, going New, and setting up a line or rake. And in this option, we can check Line. We're going to use two endpoints to define the line. So our first one's going to be at 0, 0, which is right in the middle of our chip. And our second point, we're going to set to 0, and then the height of our domain, which is 15 millimeters. Go ahead and click Create. And we can now go over to the line that we just created, right click and go Add to Active Window. And we can view our line going across our entire domain here. to make sure that we defined it correctly. Next thing we can do is we can come down here under plots. We can go to XY plot, right click and go new. And we're going to call this temp plot. And for our y-axis, we're going to define the y-axis as the static temperature, and the x-axis we can leave on our direction vector. And we're going to come down here and select our line because we want to look at the temperature across that line. So we'll go ahead and click Save and Plot. And so what we can see here is based on how we define the coordinates, our 0 is going to be on the right here, and we're moving in the negative x direction. So you can see our temperature is the hottest through the chip and pretty consistent. And then immediately outside the chip, it dips down as the natural convection takes that heat away. And as we move further into the domain, we can see that cool air returning down the far side of our domain as it returns and circulates back around in our enclosure. With that same line, we can also plot another plot of our velocity across our domain. So we can call this velocity plot. For our y-axis function, we can select the velocity, and let's look at the velocity specifically in the vertical or the y direction. And again, select the line and save and plot that as well. So we can see the same thing here. It's flat at 0 as we go through our chip since this is a solid domain. The change in density in our natural convection is increasing the velocity as we go over top our chip. As we move into our middle domain, it goes back to 0, and then on the far side of the domain drops back down. I think we'll leave the post-processing at that. If we want, we could also close out of Fluent and do the same post-processing in CFD Post, which gives us a few more options than we can do in the Fluent post-processing. But for the purpose of this tutorial, I think I'm going to leave that there. So to wrap up, today we looked at a very simple 2D analysis of looking at electronics cooling using natural convection or passive cooling in a closed enclosure. Like I said before, you can easily extend this into 3 dimensions if you want to look at a more representative 3-dimensional geometry. Maybe add a heat sink, maybe try some different chip powers, so increasing that volumetric heating rate and seeing how that affects your simulation. And again, as I mentioned before, if you want me to set up that 3D model, just leave a comment and I can go through a walkthrough of that one as well. So with that, I would like to say, as always, please like, share, and subscribe to the channel. Thanks, guys.